So the second method that we're going to look at for model selection is a method known as cross-validation. And cross-validation is a type of sample validation in which you regress to a test data set. Regress to a training data set. And then you evaluate or you score your model based on another data set. So, and I guess this general class of methods is relatively simple, but very robust, especially for models done for prediction. So with cross-validation, CV, you typically don't have multiple data sets to do training and testing. So with cross-validation, you have one data set or one sample, and the first thing is you leave part of the sample out, and then you regress to the remaining measurements, so you regress to the part that you leave in, and then the third is you compute the mean square prediction error, and that prediction error is to the data that you left out. So again, you produce a model based on the measurements that you left in, and then you evaluate the model based on the mean square prediction error to the part that you left out. And that mean square prediction error is the sum from I is equal to 1 to n out, the number of measurements in d out of your model from d out. So you sum the squared deviation and then you divide by n out. So the idea is, let me see if I can illustrate the idea. So here we might have our x values of our data points, and then here's the part we're going to fit, d. And say we have some measurements that look like this. Whatever they look like. And the open circles are what we've left out. And the closed circles here are what we've left in. And so remember, our data can be represented by a true model, which we're trying to estimate with our regression. But we also have noise. We have parts of the data that are not explained by our true model. And we can assume, for example, and so in many cases that noise is random. So the idea here is that the mean square prediction error will be large if the model is fitting a large part of the noise. That is, if it's overfitting the data. Right? So you can imagine we have these data and we produce a fit to the training data set, and if it's super well fit, then we might produce a model that looks like this. But you can see that since we have noise here, we have some, when we compare the model to the data set that we've left out, we're going to get some large errors. So conversely, MSE will be large if the model sort of misses the true model. And that could happen, for example, if we underfit the data. So you can imagine, if we fit the solid points to a very simple model, we might get something that looks like this. But this too will produce bad misfits to the test data set that we've left out, right? So the idea is to repeat this k times, removing different parts of your data, and you're redefining D out every time you do that. And then the score, or I should say the best score, which defines the best model, is the minimum of the mean square prediction error. So that's the general picture of the method, and a qualitative sort of description of why it works. So there's a couple of approaches for doing this. So approach one, I guess one approach is exhaustive cross-validation. And this is to test all possible combinations, and that's a key word, of D out. So say you leave P measurements out each trial, and and D has a size of n, then k, the number of tests you're going to do, is the number of combinations of n, of p p data set, p measurements that you leave out of n. Number of combinations of p measurements out of n. And so this is a very robust method, but the cost is that k can be large. And so that for large models or complicated models, this can be computationally expensive. So what we're going to do in this class is do what is known as k-fold cross-validation. And the overall strategy there is to divide your data set, your D, into k equal-sized partitions. I should say randomly divide into k equal-sized partitions, and then regress and compute the mean square prediction error k times, and then average. So let's consider an example. Let's say for now we'll just say k is equal to 3, and I'm going to work you through an example where we have a relatively small data set with 6 samples in it. So initially we have our data set D, and we can visualize that as having 6 values. 1, 2, 3, 4, 5, 6. And from there, let's randomly perturb the order of those samples so we get a perturbed data set. And so that data set, again, is just the same data set scrambled. 1, 2, 3, 4, 5, 6. So we might have something like we scrambled the data so it's in a slightly different order. So we randomly shuffle our data, and then the next thing is we need to divide it into k partitions. And so we have partition 1, partition 2. So this is really going to be D out 1, and this is D out 2, and this is D out 3. So for our first test, so D in is going to be everything not in D out, so that's going to be data points 6, 4, 5, and 1. And we regress to D in, and we get our first model coefficients, and compute MSPE1, and then we repeat this where D out, using D out 2, so D in 2, I guess this would be D in 1, this is D in 2, is 2, 3, 5, and 1. 2, 3, 5, and 1. That's the part that's remaining after we remove D out 2. And we regress to D in. We find the model, the second set of model coefficients with this new training data set, and then we compute MSPE2. And then we do that one more time for D out 3. And this time D in 3 is 2, 3, 6, and 4. And we regress to that data set to compute our third model, set of model coefficients, and we compute MSPE3. And I did want to reemphasize that every time we compute the error, we're computing the model error based on a fit to the data we've left in, and we're computing the error to the data that we've left out. As a, we're evaluating the predictive power for each of these tests, for each of these models during each of these tests. And then to get our model, we just take the mean of our 3 model coefficients. Where I guess this is our mean model coefficient vector. And then likewise, our mean MSPE is simply the mean from each of our tests. Oh, and we have to divide by k, the number of tests that we did, which is k. Okay, so I should note that we've done this for a given set of model coefficients. So, if this was a line, there'd be 2 model coefficients for the slope and intercept, and we would go through this exercise and produce our mean line and our mean score for a fit using a line as the basis functions. But we're doing model selection, right? So the idea is to try this for, repeat this exercise for different numbers of model coefficients. So we want to put this in a loop where we repeat for different numbers of model coefficients. And again, the number of model, the complexity of the model tends to increase with the number of model coefficients. So if we repeat this for multiple sets of model coefficients, we want to compare the values of the mean MSPE and the model coefficients, or I guess the model, which is defined by the coefficients, with the lowest MSPE mean is the best. So it's most likely to be the best predictor of the process that you're trying to, or the data, or this type of data that you're trying to understand. Okay, so that's a summary of k-fold cross-validation.